Today, we're going to trace the incredible, invisible superhighway that brings power from a massive plant across hundreds of miles and right into the palm of your hand. Let's dive in.
You know, when you plug in your phone, it feels so normal, right? But what if I told you that simple little act is the final step in an absolutely massive, continent-spanning journey of engineering? It's not just a cable, it's the finish line.
And believe me, it is a wild ride. It all starts at a power plant. Then, it gets this huge jolt of voltage from a transformer, zaps across the country on these giant transmission lines, hits a neighborhood substation to get powered down, and then has to navigate a whole maze of local wires just to get to you. It's a lot.
Okay, I know that sounds like a ton of steps and maybe a little overwhelming, but don't worry, we can actually break this whole thing down into 4 main parts. Let's lay out the map.
At its heart, the entire electrical grid is really just about 3 things. First, you've got to make the power. Then, you've got to move the power. And finally, you get to use it. That's it. Create it, move it, use it.
And this entire network, this whole shebang, it has a name. It's called the power system. Think of it as the complete life story of an electron, from the second it's born to the moment it lights up your screen.
All right, so here are the 4 official stages of that journey. This is our roadmap. First up is generation. That's where the electricity is actually made. Next is transmission, which is like the long-haul trucking part of the trip. Then you have distribution, the local delivery to your street. And last but not least, utilization. And guess what? That's you, right now.
Okay, let's zoom in on that middle part. Transmission. I want you to picture a giant electrical superhighway. Its only job, its entire purpose, is to sling massive amounts of power over hundreds, sometimes thousands of miles, and to do it without losing much along the way.
So what's the secret sauce here? How do they do that? It's all about incredibly high voltage. We are talking hundreds of thousands of volts. By cranking the voltage up to these insane levels, you can push that power across the country with almost no energy loss. Now, I want you to burn this into your brain because it's the most important part of this whole explainer. High voltage means low loss. Got it? High voltage, low loss.
All right, so the power has been cruising down that superhighway for miles and miles. Now it's time to take the exit ramp into your neighborhood. This stage is called distribution, or what engineers often call the last mile. And you know what? This is where everything gets complicated.
So let me ask you a question. We've got making the power, moving it cross country, and then delivering it to your house. Out of those big steps, where do you think the grid is the most wasteful? Where is the most energy just, poof, lost as heat? You might think it's in the power plant or on that super long journey, right? Nope. The answer is the distribution system. Isn't that wild? The shortest part of the whole trip, literally the wires running down your street, that's where we waste the most energy.
It's a huge paradox, right? The system is brilliant for hundreds of miles, and then it kind of falls apart in the last one. So let's get into it. Let's decode exactly why this last mile is so leaky.
I mean, it just feels totally backward, doesn't it? The super long distance part is incredibly efficient, but the final sprint to the finish line, that's where all the energy just bleeds away. So what's going on?
Well, the answer comes down to a fundamental rule of physics. It's called I²R loss, or sometimes just copper losses. And if this story has a villain, a main culprit for all this waste, this is it.
Okay, don't let the formula scare you. It's actually super simple. I just stands for electrical current, and what this formula tells us is that energy loss doesn't just go up as the current goes up. No, it goes up by the square of the current. So think about this. If you double the current flowing through a wire, you don't get double the energy loss, you get 4 times the loss. It's an exponential curve that shoots straight up. And that little detail, that changes everything.
And here it is. This is the whole puzzle laid out right in front of you. Remember what I told you to remember? High voltage, low loss? Well, the transmission system uses crazy high voltage, so the current is super low, and that means the losses are tiny. But then, to make the electricity safe enough to actually come into your house, the distribution system has to drop the voltage way down. And what happens when the voltage goes down? To deliver the same amount of power, the current has to skyrocket. And what does high current mean? You got it. High current means huge losses. It's a trade-off, and it's a leaky one.
Now, that high current is definitely the main villain, but it's not acting alone. It's got some accomplices. You've got things like inefficient motors on the grid, just the sheer length of all those neighborhood feeder lines, technical stuff like leaky transformers, and even non-technical stuff like, well, people stealing power or meters not working right.
Okay, so we've gotten into the weeds a bit with the physics. We see the problem. But let's bring it all back. Why does any of this matter to you? Why should you even care about this last-mile problem?
Here's why. Every single watt of energy that's lost as heat in those wires is energy that had to be generated somewhere. That means more fuel burned at a power plant. And you know what else? It's energy you are literally paying for on your electricity bill that you never, ever get to use. It just vanishes. So it's hitting your wallet, and it's hitting the planet for absolutely no reason.
And here's the final thought I want to leave you with. Our world is becoming more and more electric every single day, right? We're all talking about electric cars, electric heating. Well, all of that puts even more strain on that already leaky, inefficient last mile of the grid. So solving this isn't just some nerdy engineering problem. It's one of the biggest energy challenges we face. And it leaves us with a really big question. What happens if we fail?